Welcome back to Miss Lisa's YouTube channel, where we talk about all things science and math. Not really, but just what I want to talk about. Like, share, subscribe, because I want 1,000 subscribers so I don't have to record and then upload. I can just upload. It'll make my life easier. So share it with your homeschool friends, share it with people who need some help in physics. This is physics, so we'll be talking about physics today. And if you are doing this as a class, we're going to do this book, which is Merrill Physics. I had to look. I've taught so many classes today. But you can, if you just like the way I explain things, you don't have to do it as a class. But this is primarily for homeschoolers to get a high school physics credit. And they can buy this book. It's an older edition book, so it's cheap. And it's a good one. Physics hasn't changed. It's no different than the new book. I'm also a public school teacher, and it's just the same. Nothing's different in it. It's just an older, cheaper book. And a lot of times homeschoolers need the cheaper books. And the public school books are good because a lot of the colleges are not taking some of the homeschool books anymore that are sold from homeschool publishers for science credits. So that's why I like to use the older public school books, because you're not going to have any problems with the colleges accepting them. So anyway, another thing I want to talk about before we get down to forces is your physics book. Those of you who are taking it for a class, it's got 31 chapters. We will not do all of the chapters. Some of the chapters are... High school physics can come in different hardness. You can have something that has almost no math at all. There's a great one called Conceptual Physics by Paul Hewitt. I love that book. I love that professor. I think he's a great person for explaining the concepts of physics. But his book does not emphasize the math at all, or very, very little. And then you can have ones that are a lot like college physics, where it's just all very, very complicated math. I like for high school math, which is what this class is, to be somewhere in the middle, where we talk a lot about the concepts and build that foundation, but we also do some math. But your book has got some math that I feel, because I tutor college also, belongs more with the college, and that you don't have to have that much math for just this high school physics class. So there'll be some of the chapters we're going to skip. A normal school year is 40 weeks. So we're going to do less chapters than there are weeks. So I've been doing videos at a chapter a week, and I will probably continue doing that. And if you continue at this pace, you will just finish your year of physics early, because we're really going up faster than I would if I was teaching it in public school. Well, if I was teaching it for a full year. Now we're on the block schedule and we do everything in half a year. So just know that if you want to slow down a little, you can do that. That we're not going to do every chapter. Or if you want to stay just right with me, and this is not too fast, how fast we've been going, then know that you're going to finish your science a little bit early, and that's great. You can work on something else that you're behind in, your math or something like that. So just to let you know that the pace we're going is a little bit faster than where it would take. Normally what I do for the homeschool kids I tutor is we do 38 weeks. We do it 2 weeks shorter because we just don't have the time because we don't meet as often. We don't have the time to go the whole 40 weeks. And we meet a lot, but we don't have enough time to do all 40 weeks. So anyway, and then that's not that much difference, but there are certain chapters that I like. If we're doing a face-to-face class, there are certain chapters that I like to spend more time on and do more labs, because they're fun and hands-on. So you can do that too. If you want to spend an extra week on a chapter and do extra labs, feel free. Just watch the pace and know, that you've got a little more room to mess with, but not too much. That, you don't want to end up having to do physics all year either. Physics is great. Maybe you do want to do it all year. I don't know. All right, so we're going to talk about forces. Forces are fundamental to physics and a very important concept. It's chapter 5 in your book. And so a force, basically you can think of it as a push or a pull. It is something that can cause movement. Your book starts talking about it on page 88. And it talks about some of the forces that you probably already know about, including gravitational force, which is the Earth's pull on you. But it's not just the Earth. It is anything with mass pulls on other objects. So even though the Earth is massive and we can tell that it's got gravity, so do you. The Earth pulls on you, but you actually pull on the Earth. Now, you compared to the Earth is nothing, and you do nothing to the Earth. Where the Earth can pull you, you jump off a building, you're gonna fall to the Earth, and that's the gravitational force. But it's kind of interesting to think about that everything has gravity. And I think we do a whole chapter on gravity later. Electromagnetic force, there is something called the electromagnetic spectrum, and it is light, not just visible light, but all the light, like X-rays and gamma rays and microwaves and infrared. And there is a relationship between that electromagnetic spectrum, that light, and magnetism and electricity. Hence the name, and we will spend more time on that also. But that is also a force. There's another fundamental force called the strong nuclear force, and I always laugh at the name of it. So let me tell you what it is. You're like, you find humor in weird things, but I think it's funny. Okay, so in the atom, gotta think back to when you study the atom. Maybe you've had chemistry, maybe you haven't, but atoms are what makes everything up. It's the thing that's on the periodic table, and it is made out of protons, neutrons, and electrons primarily. There's subatomic particles, quarks, all that stuff, but we're not talking about that, just protons, neutrons, and electrons. And if you remember, in the nucleus, it is protons and neutrons. Protons are positive, neutrons are neutral. Around the outside in orbital clouds are electrons. So you will also remember from physics and chemistry and science in general that likes repel and opposites attract. So like a north end of a magnet and a south end of a magnet will attract each other, but two norths will repel. Same thing with electric charges. Two positives repel where a negative and a positive will attract. Now, this is the big thing though. The nucleus of the atom is the small little dense core that has the mass in the center, and it's all positive charges. And likes repel. So there is a force that holds those likes together. It's like taking a magnet and sticking it together. We don't know everything about this yet, but we do know that it is very strong because it's holding these atoms together, and that it seems to only work over a very short distance. So I just think it's funny. I mean, what do we know about this force? It's strong. What should we name it? What if we call it the strong force? It just seems like there would have been a better name. Name it after who discovered it? I don't know. It just seems like somebody was running late when it was the day to name the strong force. The other one is the weak force. If there's a strong force, there's a weak force. And it also has to do with the fact that some nuclei, the nucleus of the atom, decay. They do fall apart, and they give off radiation and those other particles, alpha particles, beta particles, gamma particles that make the Hulk into Bruce Banner into the Hulk. But anyway, it has to do with that. And we will talk more about nuclear reactions in this class. Nuclear chemistry is one area that is claimed by both physics and chemistry. So you learn about it in both. You get to learn about it in both classes. Not that you have to, but you get to learn about it in both chemistry, physical science, and physics. We'll talk about all of those. But that's not really what we're talking about today. What we're talking about today are just the regular things you think about with a push or a pull. A force. So we're going to first talk about Newton's 3 laws of motion. So Sir Isaac Newton lived a long time ago. He's the one who, and he was amazing. He was the first one to understand gravity. Not that what goes up must come down. No, he was the one who started realizing that gravity was a force, that it was what makes the planets go around the sun, that that the Earth is, that everything has gravity. It's way more than that. Gravity is one of the laws. It's so true, it's math. So he figured that out. He also figured out calculus and his 3 laws of motion. So he's one of the most brilliant people ever. And he did a lot of this during the plague. And during coronavirus, I have not done anything anywhere near what Newton did. So hats off to Newton there. So his 3 laws of motion, the first one is that an object in motion tends to stay in motion, an object at rest tends to stay at rest, unless acted upon by an outside force. So you throw a bowling ball. You don't have to keep pushing it to get it to go all the way down there to the pins. It just keeps going. Now, would the bowling ball go forever? Nope. Eventually it would stop because of friction. Because friction is, there's all these little bumps. No surface is completely smooth. There's little bumps on it, and the hills on one surface and the valleys on the other will fit together, and that causes things to stop. So this is what I always do to get you to remember about friction. And if I did this long enough, what would happen to my hands? They'd heat up, wouldn't they? So that is a transfer of energy going that we find with friction. So if we were in outer space and I throw a baseball where there is no air to slow it down, what should it do? Go forever until some meteor hits it and makes it do something and explodes it or whatever. But an object in motion tends to stay in motion. An object at rest tends to stay at rest unless acted upon by an outside force. So in front of me, I have my calculator. You can't see it. It's right there. But I do not expect that calculator to get up and dance around the room because I'm not in a Disney cartoon, and it is an object at rest. It will stay at rest unless an outside force, my hand, acts upon it and picks it up. So that is Newton's first law of motion. His second law of motion is really a math equation, and it is F equals ma. Force equals mass times acceleration. So where the force comes from, it comes from 2 parts. It is mass and acceleration. It's why people buy brass knuckles, weighted fists, because then they could have more force. They can accelerate their fist the same amount, but increase the mass, it's going to have more force. And in fact, a lot of physicists say that this is the most important formula in physics. And I even knew of a college physics club that they had their t-shirts made and they just put on it F equals ma, because they said that's the most important formula. That's what we're going to put on our t-shirts. And people were walking, F equals ma? Why do you have shirts on about your ma? Because they didn't understand the beauty of F equals ma. Force equals mass times acceleration. Okay. And, and you know that what I'm doing now is I'm going to do one video for the concepts, and then I'm going to go back and do the math video where I go through it and where it's zoomed in on my calculator in the math, and I'll show you the math. So we're going to skip some of these F equals ma formulas until we come back. And Newton's third law of motion is for every action, there's an equal and opposite reaction. You can think of it, I always think of Dr. Hewitt, the guy I was talking about. He talks about that, imagine you're trying to punch a piece of tissue paper. You're not going to get much punch there. But if you go punch a brick wall, you're going to have a much bigger punch because for every action, there's an equal and opposite reaction. The tissue paper is not going to hurt your hand. The wall is, because there's an equal and opposite reaction. A really good way to think of this too is, you ever been swimming and you had a raft and you go out there and you stand up on the raft and you're going to dive off of it. So you try to dive off of it, but instead the raft slips out from under your feet, because for every action there's an equal and opposite reaction. And so you're trying to jump forward, but the raft is not stable enough for you to push off of, so it slides out from under you, the reaction. Another one to think about is you blow up a balloon, you let it go, without tying it, it's going to fly out the room. And what's making it fly is as the air comes out, it makes the balloon go forward. For every action, there's an equal and opposite reaction. Another one is there are sprinklers that go I had a picture of one, but I was going to show physical science. But anyway, as the water spurts out, it kicks the sprinkler back and it makes it turn around. My dad used to have one. It was called like a whirly bird or something, or rain bird. It was a rain bird. That's what it was. And it was a sprinkler that turns around so it wasn't the kind that went shh. It was the kind that went in a circle. And it used, for every action, there's an equal and opposite reaction to make it turn. It had no motor. It was just doing it using that force. It was using Newton's 3 laws. Okay? Now, what is the difference in mass and weight? There is a difference. It's kind of the same on Earth, but there is a difference. Weight is the pull of gravity on something. So on Earth, I stand on a scale and gravity pulls on it and I see how fat I am that day. But if I took me to outer space, then there would be no gravity pulling on me, but all my fatness would still be here, and the amount of matter that makes me up would still be here, and my mass would be the same. So mass is the amount of matter, weight is the pull of gravity. Your mass does not change upon location, your gravity does, your weight does. Now on Earth, the gravity is always the same. We don't have more or less gravity, and most of us are not astronauts and space travelers. So in general on Earth, a lot of times they're a little bit interchangeable. I know there's physicists going, no, but hear me out. And in particular, we have a scale which works on gravity, like standing on my bathroom scales. That is a scale working on gravity that's telling me my weight. And then if you have a balance, like 2 pans that you're comparing like a kilogram weight to, then that's a balance, and it would work the same whether or not you were on Earth or on the moon where the gravity is different. My spring scale wouldn't. I would weigh much less on the moon. In fact, I think I'd only weigh 1/6 as much as I do. It would be a terrible weight to have on Earth. I'd be dead if I weighed that. But on the moon, I'm only going to be 1/6. So, okay, so that's the concepts. Now, but what we do in science is we will call it a mass, we will call it a balance, but the device we have is actually a scale. It would not work on the moon, and it would not give you the same reading. It would give you a reading of 1/6 if you took that to the moon. So I teach public school too, and in my room I have a bunch of these. We call them balances, but they're scales because they are using gravity to push on the little pan to weigh the thing. Now they're doing it in a unit of mass, which is grams, kilometers, things like that. That's a unit of mass. Where pounds and newtons are a unit of weight, but it's because on Earth they're really the same concept, and so we'll call it the fancy right thing. We'll call it a balance when it's really a scale, and we'll put it in the right units, grams and kilograms. But it's really a scale. So that if that didn't make sense to you, that's okay. It's just that in certain problems we will use newtons and we won't use pounds because that's English. Well, but in other things, when it's a mass, we will use kilograms or grams. That's the big takeaway there. And the weight is mass times gravity, and we'll do some problems with that. So our formula is F equals ma. Now, different kinds, let's see about that. Okay, so I already told you about friction, and there are different kinds of friction, and you know this. You've been living in the world doing experiments, whether you realized it or not. You push on something, trying to get it to move, like a sofa. Once you push it and get it moving, it's easier to keep it moving than to start it moving. what you had to overcome to get it to start moving is called static friction. And it's because those hills and valleys are really squished in there tight. Once you get it going, it's just touching the mountaintops, and that's called sliding friction, and it's less. Static friction is more than sliding friction. Once you get it going, it's easier to keep it moving. But the easiest of all is if you can go get hand trucks with a wheel on it, and then it's rolling friction. And you can even see with your fingers as you roll one group across the other that would be the least of all for the friction. Now, what can decrease friction? Well, things like oil, graphite, things that are going to make it where things slip by each other more easily, decrease friction. It's a very important thing. A lot of our machines lose all of their energy to friction. Your car, for example, the gas you put it in, only about 20-30% of it at most go to actually make your car go. All the rest of that gasoline is wasted as heat energy. Because of friction, it causes parts of your engine to heat up. Every time your car goes, you put your hand on that hood, it's going to feel warm. So if we can reduce friction, then we have more efficiency in our machines. And if you leave the oil out of your car, your engine is going to seize. It's going to lock down because there'll be so much friction between the metal parts. They'll heat up so much that they'll start melting and bending and fusing. And you will destroy your engine. My husband did that once. He had an old Toyota Corolla station wagon, and he put oil in at the gas station, forgot to put the cap back on, and it blew all the oil out, and the engine, and so then it didn't have any oil in it. He worked a long way away from home, and by the time he got home, the engine seized and locked, and we had to just get rid of that car and get something else because it already had like 300,000 miles on it. It wasn't, so we could have dropped a new engine in it, but by then other things were wearing out in this car. It'd be a good car. People called it the Monkey Mobile. I don't know why, they just did. It was a cute little car. All right, so now we calculate friction, and we'll do this in some of the problems, but the equation is F equals, the friction equals mu. It is a Greek letter. It's like a cursive U with kind of long tails on it. And then, anyway, it looks like it says F equals UN. So it looks like it says fun. And it is the force, the normal force. Let me explain to you what that is. When like gravity is pulling down on my calculator sitting on the table, the table is holding it up. It is the opposite of gravity. And it is called the normal force. If gravity pulled more than the normal force, then the calculator would go through the table. If the normal force pushed more than gravity, the calculator would go flying through the air. But they're balanced. They're balanced forces, and the calculator is sitting right there. It's not moving. All right, so a lot of times in physics classes, that is shown as a big N. Your book does it F sub N. I'll show it to you in the math video. But anyway, it's how you calculate friction. And mu is called the coefficient of friction. It is a constant based on, is it static friction, sliding friction, rolling friction, and is the material. So something like a piece of sandpaper has a mu higher coefficient of friction than a piece of wax paper. It would have a lower mu. All right, so we're going to do a problem with that. There's a fun little lab on page 98 that you're going to do as part of your homework. You need a spring scale to do it. A fishing scale would work. If you got one of those scales you hang your fish on and see how much it weighs, that would work. That's a spring scale. But you need a spring scale for this class. We use them a lot in here, so you need to get one. But that's your fun little lab we'll be doing this week. Net force is all the forces added up on something. So we'll be doing a problem with that too. talking about elevators. That's your lab. So another thing that it talks about in this chapter is the fall of bodies in air. So if something's falling in air, it gets faster and faster and faster because of gravity. In fact, it speeds up at 9.8 meters per second squared. But it doesn't speed up forever. Eventually, drag or air friction will make it where it's still falling, but it's not speeding up. It's not accelerating anymore. So like when I was a kid, I remember hearing that if you throw a penny off the Empire State Building, it'll get faster and faster and faster, and it'll become a bullet, and it will kill somebody down on the sidewalk. Not true. If you throw a penny off the Empire State Building, it will get faster and faster and faster until it's got so much air resistance, so much drag that it is not speeding up anymore, and it's not going fast enough to be a bullet. To be a bullet, it's got to be fired out of a gun, not just thrown. And so if you got hit by a penny that went off the Empire State Building, it would cut your skin, but it wouldn't even break your skull. So it would hurt, and you shouldn't do that because it's mean to cut people with pennies. But it would not kill them. So another thing is, and I thought it must have been a different class because I thought we talked about this last week. But is if you ever find yourself jumping out of an airplane without a parachute, for one reason or another, that there are people who have actually survived this. People will skydive and their parachute not open. People have had plane damage where they got sucked out of a plane and lived. Now, most people die, but there have been people who lived, and there was, the way they did it was by spreading out, trying to make themselves as big as possible so that they stop speeding up where they're only going one speed. And then the other thing is, what kills you is a sudden stop. So if you can make that stop go any extra length, you won't die. The one person I knew, like personally, I knew this person's brother, who she was in a parachuting accident. Her chute didn't open. She landed on a barn roof and then rolled down it. So instead of just stopping, she was able to roll down the roof and then fall off the barn. And I think she got a broken bone, but other than that, she was all right. People get broken bones falling off of a bicycle. So she, no brain damage or anything. I've also heard of people hitting trees, and as the branches are break, that slows them down, and they were okay, maybe a broken bone. And also, there was someone who, when they fell, they landed in freshly plowed earth that had been plowed commercially by the big plows that go really, really deep, and boop, they were okay. Also, and this is not coming out of a plane, there was a guy who fell out of a skyscraper on his bachelor party. So he was drunk. Okay, which they say drunk people survive stuff because they're more relaxed and it helps them, like car wrecks and stuff. But he fell out a window because he was drunk. He fell many stories that would like kill you normally, but he fell through bushes and he was okay. He was scratched up. And that actually happened to me too. I was not drunk, but I was in college, and as a service project, we were cleaning an old building that was multi-stories up. And so I'm cleaning this window, and I do it with too much enthusiasm, go figure, and I fall out of the window. But I fell into some bushes, and for a long time I had a scar right there where I got stabbed by one of those things, but I was okay. I was like, oh. But I went and told him, I fell out the window, I'm going home. No more service project for me. I'm done. But I fell out of the Philo building at Erskine College, and lived. And it was like maybe about 3 stories. It wasn't that many, but if I had hit concrete on my head and stopped suddenly, it could have definitely caused some damage. If I don't know if death, but definitely damage, more than just a little poke by a bush, a little cut. But I wasn't happy, and I went home. I didn't do any more work that day. All right, so you'll read about that, about falling bodies in air, and that's it for chapter 5. So come back and see part 2. Like, share, subscribe. I'm trying to get 2,000. This is Miss Lisa's channel, and science is great.